Well, nice to see everybody. Welcome back to class. Let's see here. In terms of announcements, your midterm is a week from today. Okay. Here's the deal. I expect you guys to be here for your midterm. That includes all of you. I don't know, like that camera, this camera, like all of you people on the internet. You should be physically here for your midterm. Um, it's the one time that I get to look out in the room and pretend like I have a full class of students. Um, if you have like an absolutely immovable conflict, you are expected to reach out by the end of today to let us know. Otherwise, we're going to expect you to be here. If you don't show up in your midterm, you're going to get a 0. The students who have accommodations, hopefully you've already filed all of your letters. We've taken note, and we'll try to follow up in the next couple days with the sorted plans that make sense for your accommodations. In terms of other announcements, so Leticia and Mark, I think, are both leading review sessions for the midterm. What are the dates? 5 to 6 p.m. This Friday and then this coming Monday. Fabulous. So I think what they've chosen to do, it's all announced on Piazza, is to divide by topic, right? So it's like roughly half and half. So that's a good way to do a review, and you guys should come prepared with all the hard questions to ask your TAs to hold them accountable. And of course, we're all working together to write the midterm right now. So, not that I'm here to give you life advice, but just in general, it's always good to go to these sessions because you might notice the people that wrote the exam tend to know the right topics to cover before the midterm. I don't think that's like a particularly surprising fact. Your midterm, you can bring one sheet of handwritten notes, front and back if you like. And other than that, it is closed book, closed phone, closed laptop, closed AI, closed friend next to you, all that good stuff. Any questions, comments, concerns? Yes. Up to and including the lecture immediately prior to the midterm. Yeah, good question. Any others? As you can imagine, probably the midterm is not going to ask you to do some complicated calculation involving the thing we just covered in class. But like, true false question or something would be fair game. Yeah. Okay, so that's that. Meanwhile, I saw some people in my office hours yesterday were doing homework 3 already, and it appears to be a lot easier than homework 2, which is great. That said, you should start because homeworks take time. Cool. All right, so with that, let's get started with today's lecture. And essentially, we're going to pick up where we left off. Remember that essentially in our previous lecture, we finally, in this course, in 67350, moved on from linear problems to nonlinear problems. And in particular, our goal in the previous lecture was to derive algorithms for root finding, right? So essentially, I'm given access to some function f of x, and my goal is to find a point x star where f of x star is equal to 0. And we talked about a few different algorithms with different assumptions, right? One of them is bisection, which is kind of like the binary search of the numerical analysis world, which requires your function to be continuous and to bracket a root, right? Remember, so like I've got some function and I'm looking for the root, like here's x star. And essentially I have some region where like at one point my value is positive, one point it's negative. In this case, because my brain likes symmetry in one step of bisection, you'll do pretty well. But essentially you divide your interval in half and each time keep bracketing your root closer and closer and closer, right? That algorithm has very few assumptions, but it had a linear convergence rate. By the way, it converged unconditionally, right? Meaning that like as long as we bracket a root, we know that eventually our error will go to 0. Then we talked about a second algorithm, Newton's method, which requires our function to be differentiable. And what did Newton's method do? Well, essentially, at every point, we draw a tangent. It's hard to draw lines when you've had a lot of copy like that. To our curve, we approximate it with a line like that. And we say, so here is our next approximation of the minimum. It's just the root corresponding to the line rather than our curve function. So they compute the Taylor series. But like, oops, lines are not great approximations. So really, we ended up there, and we iterate. Right? So if we want to compare these two algorithms, we can do so. So essentially, what did we show in our last lecture? I wrote all the right equations, but I could have articulated it better. So I thought I'd spend a minute summarizing. You might notice the last 5 minutes of class, suddenly I panic and start jamming a bunch of stuff that I have to redo the next lecture, and I should stop doing that. Okay. So what do we show? We showed that essentially this is an unconditional convergence, meaning that like so long as I bracket a root at the beginning of this algorithm, I will converge on a root if my function is continuous, right? And we showed in class that this is a linear convergence rate, meaning that if ek is the error between my estimate of the root at step k, then we prove some upper bound, which is that it's less than or equal to some constant. Ek is less than or equal to some constant times ek minus 1, and moreover that constant is less than 1, which is good. For Newton's method, the story was a little more complicated, right? So what did we show? We showed that it converges in some neighborhood of the root. And essentially the way that we did that is we showed that fixed point iteration on differentiable stuff converges so long as the Lipschitz constant of that function is less than 1, right? And what we showed is essentially that, okay, so Newton's method can be understood as fixed point iteration. Namely like, okay, so think about the root here. If I linearize about the root, and I take the root of that linear function, I get 0 again. So that's the fixed point. And at that point, our function has a 0 Lipschitz constant, meaning that like essentially in some little neighborhood around that point, I converge. Now, one thing we didn't say is how big that neighborhood is. And so in fact, in practice, getting Newton's method to work for root finding is a little annoying. Like you have to have a pretty good guess of the initial point, and there's not necessarily a very good procedure for doing that. And moreover, we showed that be a little bit careful, and this is where I feel like the words that came out of my mouth can be a little better. So let's see if I can do it again. This inherited the linear convergence rate that we showed for fixed point iteration so long as it converges. So within this entire neighborhood, if it converges linearly. And then moreover, what we showed is a quadratic convergence rate. And here's what's a little bit tricky. The quadratic convergence rate is when you are sufficiently close to a root, right? So essentially, we showed a bound that looks like the following. Ek is less than or equal to c, ek minus 1 squared. One thing that we didn't do is bound that c. Like over here, we knew that c was less than 1. So like it feels a little bit uncomfortable. Like if c is 75, that feels like that could be an issue, that like maybe my bound is too loose. And so here's the reasoning, and this is the like sentence that was kind of missing from the last lecture. We know that it converges linearly. So if I wait long enough, my error is going to be small, right? Eventually, small numbers squared are even smaller, right? So once I am in that regime where the product of these, I guess, 3 things is like less than 1, then now I'm cooking with gas. Like now I converge quadratically, right? So kind of the way to think about it, I see your hand, I'll come back to you in a second, is like as a function of k, there's like a phase where it might be converging linearly, like the error is just going down a straight line. And then I get close enough where the bound that we derive for Newton's method is relevant, and then suddenly the error starts to drop really fast. Now, because of that, and just like from a terminology perspective, what we say is that assuming Newton's method converges, right, we have to be a little careful how we say it. So it's a conditional convergence situation. It converges at a quadratic rate. And the reason for that is that we only care about these things asymptotically as k goes to infinity, right? And so like it could be that for some fixed number of iterations, the convergence is pretty crappy, but then eventually we get in this regime where I'm close enough to the root that the convergence gets really fast. And basically what we showed in our lecture is so long as our function is differentiable and simple, meaning that essentially, oops, sorry, let me hop forward a little bit. I'm talking and not tracking on my slides. Yeah, so long as we don't have f prime equals 0, which is like a particularly bad case for Newton's method, I'll show you in a second, we converge quadratically in some little neighborhood. Okay, so the idea here is that like there's maybe a phase where convergence is slow or linear because you just are doing fixed point iteration. Eventually you get close enough where that squared number is really small, and then shoop, your convergence goes really fast. Yes? That's a funny question. Yeah, is there one might hope where there's like a really small neighborhood where it converges cubically. The answer is no. Like we didn't prove a bound like that. There are other algorithms that have that property. There tends to be a trade-off, I think, kind of spiritually between the size of the neighborhood and when these bounds kick in. So like, for example, I mean, how do we do Newton's method? We essentially like wrote a Taylor series and then took its root. So you can imagine like expanding that Taylor series and doing a better job, which at least in 1D you can do, right? Like parabolas, we can find their root. I believe that algorithm has a name. I forget what it is. And indeed, the convergence rate is cubic, but what tends to happen is it's cubic in some little itty-bitty neighborhood around your point. So these things tend to be only relevant when you like want really high precision. And moreover, you have to have access to all the derivatives of your function. In general, Taylor series tend to be very good approximation next to a point, and as you get bigger and bigger neighborhood, they can go pretty crazy. So later on in this class, we'll talk about polynomial interpolation. And essentially what can go wrong is if you have small errors in the coefficients of a polynomial, it'll look okay in a small neighborhood, and then as you go bigger, they'll get oscillatory and crazy. Yeah, great question. Any others? Cool, so we now have two root finding algorithms. One that converges linearly and makes very few assumptions on our function, just continuity. This thing could be non-differentiable. I suppose it could be differentiable almost nowhere, or whatever the right phrase is if you're a math person. And we have another one where if I have sufficient number of derivatives and I have a pretty good guess of my root, then I can do even better. By the way, Newton's method is going to be the sort of foundation of optimization algorithms we'll talk about soon. Now, here's one mild headache, which in one dimension isn't such a pain, but in higher dimensions we're going to see is really problematic. Notice that we needed another ingredient to run Newton's method. It was not enough to even just know that my function f is differentiable. Not only do I have to know that f is differentiable, I need access to the derivative, right? So for example, if I implement a function f of x in code, which is a very typical thing to do, at least until a couple years ago, most people's code could not automatically output the derivative along with it, so then you'd have to ask your software engineer to implement that formula as well. And moreover, that's additional computation time. And so that could be an issue. Now these days, because of like automatic differentiation is a sort of tool du jour, that's becoming less of a problem. But even so, like essentially, one thing that you should note is in each step of Newton's method, you need kind of two taps of your function, right? You need to evaluate f and you need to evaluate f prime. So actually the complexity of each step takes kind of two calculations instead of one. And for complicated functions f of x, that could be a mild problem. This is all in 1D, but this is all kind of predictive of the high dimensional story we're going to tell in a minute. So what are we to do? Well, there's one additional algorithm that I think you guys should be familiar with, which is really sneaky. I love this technique. It's so cool. We're just going to draw a picture of it because I think you guys could all fill in the mathematical details. And this algorithm says the following. So let's say that I'm optimizing some function. I'm going to draw it a little strategically. If you might notice, like these algorithms look really pretty if you draw your function just right. And then unfortunately for us, that doesn't always happen. So let's say that my optimization algorithm in the last two iterates had these 2 points. We haven't even defined what our algorithm is. Maybe I run Newton for 2 steps or whatever, and I get 2 points. So here's like, you know, maybe xk minus 1, and here's xk. Now, if I wanted to do Newton's method, I would linearize my function about this point. Here's a different thing I could do, is say like, well, what's a reasonable approximation of slope of my function? Well, I kind of have staring at me 2 points, like a dx and a dy. So rather than drawing the tangent, I could instead draw the line that goes through the previous 2 iterates, like that. Does that make sense? This is called a secant. Now this line is not tangent to my function anymore, but it actually is a pretty reasonable approximation. So think about what happens as Newton's method converges, for example. These points get closer and closer together, and that's exactly the regime where like divided difference is a pretty good approximation of a derivative. And so like, essentially what does secant method do? It's exactly the same as Newton's method, but every time I need f prime, rather than computing f prime, I just compute the following approximation. It's like roughly equal to f of xk minus f of xk minus 1 divided by xk minus xk minus 1. Yeah? This is an approximation. Well, here's the kind of good news. How much effort does it take per step of this algorithm as opposed to Newton's method? Well, now I don't have to evaluate f prime. And moreover, I can just kind of keep around the f from the previous iterate. So I've like kind of divided the effort per step in 2. Does that make sense? And this gets around the matter of needing a derivative. In fact, I believe under slightly weaker assumptions, you can make this algorithm work, even if there are like points where your function isn't differentiable. So this is a technique called secant method. I don't think there's a reason to go through all the steps of the derivation because it's essentially the same as Newton. It's just you substitute this approximation for f prime. One thing that we're not going to cover in this class is like what is the convergence rate of this iteration relative to Newton's method. So remember, Newton's method is quadratic. What's it called? Bisection is linear. Fun trivia fact that you can share at like bar trivia someday. The secant method converges somewhere between those two things. In fact, for whatever reason, the convergence rate of secant method is the golden ratio, which I'm sure like to people that like do spiritual math with like the spiral thing, like it's very meaningful. Do you know this Instagram website where they just like take weird meme photos and put the golden spiral on top? No, it kind of like it speaks to me. In any event, the convergence rate of secant algorithm is the golden ratio, which is somehow magical and spiritual. The proof of this is not particularly hard. It's just like an analytical thing with a bunch of bounds. But I've never found it to be particularly enlightening. If any of you guys finds an intuitive proof for this, let me know. I'll put it in the textbook. But all this is to say that this algorithm is like closer to quadratic than linear. Notice it's 1.6. And moreover, actually, what people often find is that secant method can be a little bit less sensitive to noise than Newton's method, which is a little surprising. But it actually makes a little bit of sense. So for instance, let's say that I'm trying to do root finding on some function, and it looks like this, right? This is very typical for lost landscapes in machine learning. What is Newton's method going to do? Let's say that my current iterate is here. Well, the tangent is actually like completely opposite the motion of this function. Do you see that? And so like a kind of intuitive advantage, I actually haven't seen a nice theoretical discussion, but I'm sure there exists one out there in the literature somewhere. Says, well, secant method doesn't look at this local error, right? It takes kind of big steps. And so because of that, you're a little bit more likely to capture the slope of this function in aggregate. Of course, there's like definitely a luckiness factor involved here, but I do think that's the mythology about this particular algorithm. Does that make sense? Okay. Now, we have these two algorithms, right? We've got, gosh, I keep forgetting the name. Bisection and Newton's method. They have different convergence rate. Bisection is somehow safer, right? Because we know that it unconditionally converges. I think a reasonable question that you can ask is like, is there some way to get the best of both worlds? Like, for example, to have quadratic convergence rate and unconditional convergence. The answer is kind of, sort of. There's a lot of algorithms out there that attempt to do this, but then actually proving that they work is quite challenging. Just if you're curious, because I always get these questions in class, there are a broad variety of methods that we call hybrid methods that try to combine Newton and bisection in some clever fashion. So for example, one thing that I could do is say that, like, suppose I have a function that, let me see if I manage to draw it correctly. There we go. Where I bracket a root and it's differentiable, so it satisfies the assumptions of both algorithms, right? And moreover, let's say that my current iterate for like Newton is here, right? Then one thing that I could do is do a Newton step like that, right? And say, oops, that's outside of my bracket, so I'm just going to throw it away and do a bisection step instead, like that, right? This is roughly what people call Decker's method. And it is safe if you want a really challenging math problem. So this obviously, actually it's not even obvious that this algorithm converges linearly or quadratically, because now I've sort of like munged together two algorithms locally, and you could imagine some really bad case where like you keep flipping back and forth and choosing the worst possible thing for the next iterate. Proving that this method has a particular convergence rate is actually quite challenging. So in any event, I don't think it's worth covering these in great detail. The number of times that you guys are going to encounter generic one-dimensional root finding problems in your everyday life is relatively small. But I think mostly these algorithms are good motivators for the high-dimensional case, which is what we'll do next. So to give a bit of a summary of the picture so far, the main thing you guys need to remember is that now that even in this one variable problem of nonlinear root finding, we no longer have any hope of solving our problem exactly. So the best we can do is sort of iteratively approximate things, which is going to lead us to like error bounds and those kinds of convergence rates, rather than like what we did when we talked about LU factorization, where we could just say in cubic time up to numerical precision, we got the answer, right? So we're like in a different universe now. There are lots of different convergence rates out there. We've now seen an example of linear, superlinear, and quadratic, for bisection, secant, and Newton, respectively. I'll leave it to you guys to derive a cubically convergent optimization algorithm, but I think those are pretty uncommon in practice. One final thing that's worth noting that sort of distinguishes between secant method and Newton method, for example, and we'll see this even more in the high-dimensional case. Now, all of you guys, many of you are reading papers in like NeurIPS, ICML, whatever, machine learning universe, and it's very typical to see these plots, probably not for one-dimensional optimization, but instead for like very high-dimensional optimization, where like your loss function, for example, does this, it kind of wiggles down. Of course, in machine learning, it's like really doing that, and then they smooth it out. And they say like, aha, like, okay, my algorithm converged, I have some low loss. And one question that you should always ask about numerical algorithms in learning, optimization, or root finding is what's the horizontal axis here? Like so far, our horizontal axis has been k, like the index of the iterate in our algorithm, right? So for example, in these bounds that we proved for bisection and for Newton's method, essentially what we're keeping track of is the number of steps it took to the minimum. Now, here's where we have to be a little bit careful. Let's say that each individual step of our algorithm took 10 times as long, right? Then if I reshape my plot so that this isn't k, but it's time, then sometimes the picture can look very different, yeah? So as an example of that, if you look at comparing secant method versus Newton's method for root finding, one of them requires evaluating f once per step, and the other evaluates f twice per step, right? So the cost of each step is roughly a factor of 2. Now, the convergence rate of one is faster than the other, but this is the kind of consideration you have to be careful about when you look at these plots and you evaluate which of these algorithms is going to be useful, that it's not just a question of convergence rate, but also the time per iteration. Like what we're going to see soon is that in high-dimensional case, every step of our algorithm is going to require like inverting a linear system or something like that. And now it's getting very expensive, right? So it might be that a quadratically convergent algorithm, unless we run it for literally n cubed steps, is just not worth it, right? And so we'll see many examples of that moving forward. Okay, so that concludes our one-dimensional root finding discussion. Any questions so far? I think this stuff is a little easier than some of the things we've done before. Fabulous. So, unsurprisingly, the next thing that we're going to study is multivariable root finding. Of course, generically, you might have a function from Rn to Rm, but one thing you can probably convince yourself is that this root finding problem really doesn't make sense unless the dimensionality of the input and the output of f are the same. Right? Otherwise, you're going to have like sheets of locations where there's roots, or generically, you might not have a root at all. We actually have studied one root finding problem, I would argue, which is as follows. If my function just happens to be ax minus b, then I know how to find its root, right? In fact, we just spent the first third of this course developing algorithms for this specific root finding problem. Now, it sounds goofy to say that, but what do you think our root finding algorithms are going to do? They're going to approximate our root finding problem with this one. We know how to find the root of this guy, and we're going to iterate, right? That's exactly Newton's method. You see that? And in general, this is sort of spiritually what's behind most algorithms for root finding and optimization. You identify like one problem whose solution you know, and then you just keep approximating the problem whose solution you don't know with the one that you do, right? So like, for example, for Newton's method, what did we do? Well, we know how to find the zeros of a line. So we approximate our function with a line, we compute the zero, but oops, our approximation wasn't any good, and now we have to iterate. Does that make sense? So good. So essentially, our goal here is going to be to find roots of these kinds of functions. Generically, you want n to be bigger than m to even have a root, but I think it's pretty safe to assume that they're equal. The textbook has a lot of discussion of these different cases. I'll let you look there. So the main object that we're going to talk about, so for one, by the way, this bracketing algorithm that we had, like bisection, is it obvious how to extend bisection if you have a function of more than one variable? I would argue no. Yeah, it's actually quite challenging. It's not even clear what it means to bracket a root anymore if you're in 2-dimension. And so actually the typical algorithms that we'll cover in this class do require your function to be differentiable at least one time. So that leads us to one more object that I'm going to dredge up from your college calculus class, and you've probably forgotten, which is called the Jacobian. This is a generic version of gradient of a function. Now remember, our functions f have a lot of inputs and a lot of outputs, right? And so essentially, what is the Jacobian? It's this giant matrix of the derivative of every output with the derivative of every single input, right? So I can give this thing a name like df, and the formula for df ij is given by the thing on the right. One thing that I always get wrong, and I'll inevitably get wrong in this course, what is the size of df for f going from Rn to Rm? Let's think about it for a second. This is one of these annoying, like if you're a category theorist, there's probably some deep reason why like indices flip around. M by n. That's exactly right. Yeah. So the way that I usually remember it, I think it's right. Yes. The way that I usually keep this straight in my head is that like the main reason that we use Jacobians is to linearize functions, right? So here's our typical kind of one-term Taylor series. If I want to evaluate f of x generically, it's roughly equal to f at some xk. You can see where we're going with this. Plus the Jacobian times the difference. This is just a Taylor series. And notice in order for this to kind of parse out, remember the output of f is going to be kind of like the number of rows of df. And so that's a reasonable way to kind of remember this stuff. Cool? Okay, so what do you think our algorithm is going to be for root finding? Well, I take my function, I linearize it by computing its Jacobian, right? So I have now an approximation of f about xk. Well, a reasonable approximation of this root is to just set that right-hand side equal to 0. And when I solve for x, which we'll call xk plus 1, I get this expression here. You can double check that in one dimension. This is the same as the Newton's method that we wrote before. So I could do this on the board, but I actually think this is pretty straightforward. Any questions so far? So one thing that is justified in the textbook, but we'll maybe skip here, is that this method is still quadratically convergent in some neighborhood of the root, but you need now some bound on the eigenvalues of the derivative to make sure that things don't explode in any particular direction. I see, yeah. By the way, as a bit of a review question for our algorithm, you could imagine an implementation of Newton's method doing the following, where I evaluate the Jacobian of my function at xk. This is an n by n matrix. And now I just invert it, and then I multiply it by f. Is that a good idea? No. Why is that? That's right. That really, this notation, like A inverse times B, is just a placeholder in numerical analysis for solve AX equals B, right? And that you don't need the whole inverse matrix. You just need the solution to this particular problem, right? And some of the methods we've seen, like if you actually store the inverse of the matrix, like 1 over x, is going to cause numerical issues that were avoidable, whereas really your code should just say solve this with f as the right-hand side. Yes, your question? How do we know the Jacobian is invertible? We don't. And in fact, there are cases where it's not. The question is the root finding problem particularly well defined in that particular case? And the answer is not really, because essentially your function remains flat in that direction, which is not so good for root finding, right? Yeah. So I think typically, yeah, for Newton's method to work, you need to make a lot of assumptions, like that f maps Rn to Rn, like your Jacobian also needs to be square or you can't invert it. And moreover, it needs to be invertible, meaning that there's no direction where like there's just no ambiguity, or rather, you cannot have ambiguity in the first derivative of your function as to like where to go to decrease and increase. Yeah, good question. So, right. So if you're curious, I don't think we're a little behind in this class, so we're gonna skip over a little bit of theory. But essentially, one thing that you can show is that so long as so remember how we proved, we proved convergence of Newton's method by first showing convergence of fixed point iteration, and then showing that Newton's method was a special case. So we just kept iterating like x equals g of x. So in this particular case, the way that you kind of extend the proof that we had in one dimension to higher dimensions is to show for the fixed point iteration case that all the eigenvalues of dg, or I believe singular value is enough, but I'd have to think about it, are upper bounded by 1. Which is kind of like, remember we had a Lipschitz constant before, right? So this is kind of like saying the Lipschitz constant in any direction is upper bounded by 1. And so long as that's the case, then we can show Newton's method converges. And the quadratic convergence case actually extends like completely the same. You can go back to your proof and you'll see that nothing really changes. Cool. So all this is to say that Newton's method in multiple dimensions kind of looks like Newton's method in 1D. In terms of convergence rate and in terms of drawbacks. Like I need a guess that's pretty close to the root in order to use this thing. Okay, so the reason I'm rushing through this is that I think Newton's method is interesting, but it also, I think, like especially remember we drew this picture like a function that is super wiggly. And like Newton's method really struggles on these particular things because linearization of your function might be like totally off from what you would hope. So I think especially in multiple dimensions, this is even more likely to happen, right? If you have any one direction where your root finding problem is a little wiggly, this algorithm is likely to do pretty poorly. So I think what's happened over time is that for root finding, unless you know a little bit more about your function, for example, the typical assumption is that it's the gradient of a convex function, but we don't know that yet in this class. The Newton's method is actually fairly uncommon relative to methods that look a little bit more like secant because they're stable and they don't require a giant derivative matrix, right? So these are all positives. And so essentially, I think for the rest of today's lecture, we're going to tackle two problems. One is differentiation is hard. Now, in one dimension, that's debatable, but in multiple dimensions, nobody wants to compute a Jacobian matrix. I can tell you, my graduate school days were before the time of PyTorch. And I spent a large part of my graduate career as a PhD student just computing ugly gradients of things and ugly Jacobian matrices. If you look at my old research papers, you'll see that. The good news is we live in a universe where we don't have to do that anymore because we have a lot of cool automatic differentiation tools. We'll briefly mention how they work later in this course. But they're still big dense matrices, right? Like the individual iterates of our root finding problem are in Rn, so we need to store an n by n matrix in order to make progress on this problem and invert it, which is quite expensive, right? Moreover, here's kind of an annoyance. So like, remember when we talked about eigenvalue iteration, we made this kind of cool observation. Like, so let's say I wanted just the eigenvalue closest to 0 of a matrix. How did we do that? We just kept multiplying by A inverse, a little bit of midterm review. And then we realized that if we prefactor A, right, like if we do LU factorization once before we launch this eigenvalue iteration, then the steps of eigenvalue iteration were quadratic instead of cubic, right? Can I apply that observation to Newton's method? No, right? Because in every step of Newton's method, I get a new df, and I just throw away my old Jacobian. But somehow that feels wasteful. In particular, like, if you look at your Jacobian matrix, especially when f is starting to converge, right, the Jacobian is probably not changing a whole lot from one iteration to the next, and yet I have not had any ability to cache a lot of the computational work that I did from one step to the next of this algorithm, right? And so all of these points on the board, you might notice I ask a lot of leading questions in this class, suggest that maybe there's some alternative out there that helps us overcome these problems, right? And in particular, we had a clue, which is the secant method, right? Which is at least a way in one dimension to avoid differentiation. Unfortunately for us, let's think about it for a second. Is it obvious how to extend the secant method if we're in multiple dimension? Probably not, right? Because now we've got these iterates that are like ping-ponging around in n-dimensional space. But I look at just the last two iterates. Well, unfortunately for me, that's not enough information to determine an entire n by n matrix, right? There's n squared entries in the n by n matrix, and I only have n numbers. And so it's not entirely obvious, like, if there's some version of secant method. Now, you could imagine a version of secant method where I keep around like the last, I don't know, I guess n iterates and construct an entire plane, but in high dimension, that'd be rather expensive. Yeah? And moreover, I don't know where you get those first n steps. And so instead of doing that, we're going to cover an alternative here. This is our sort of warm-up algorithm, actually. So like in a couple lectures, we're going to talk about an algorithm which is dominant in engineering and computer graphics, a little bit less so in machine learning because it's sort of a medium-dimensional algorithm called BFGS for optimization. Has anybody ever used an optimization toolkit and like it just automatically pops out like using BFGS and then it runs your code? Yeah, I see a few hands. I know Leticia has, but she didn't raise her hand. We're going to cover the BFGS algorithm, which is like a souped-up version of the algorithm that we're going to cover today, which is some version of secant method that works in multiple dimension. This is super cool. I think these algorithms are so clever and beautiful. And by the way, this is really like, this is a graduate course, and like arguably the first third of this class is pretty undergraduate coded. This is now, we're in graduate land. Sorry. So put on your seatbelts. And in particular, we're going to cover an algorithm called Broyden's method, which is for root finding in multiple dimension. What we're going to see is that extending Broyden's method to optimization is going to be kind of easy and kind of hard because now we'll know that our df is symmetric matrix because it's the Hessian of a function, for those of you who are previewing for future. And basically, Broyden's method is built on the following. Oh no, my notes fell asleep. When I had my notes on paper, they didn't fall asleep. But now they do. Okay. Which is as follows. Let's say that I have a function, for example, in R2, like on the plane. Now, if I'm on the plane, there's the plane. You can tell because I drew a rectangle. And I'm at some particular point, x. You know, in general, the function varies as I move x horizontally and vertically. And both of those are captured in the different elements of df. Okay? But now, like, essentially what we're looking forward to are methods where I just have f at one additional point, right? That's kind of like what secant method does. The question is, what information can I get out of that? And in particular, one thing we can do is define an object that is really critical, which is called directional derivative, which is going to do the following thing. Let's say that I'm at a point x, and moreover, I have a vector v. By the way, a year from now, if you take my geometry class, we're going to spend like hella time analyzing this object and seeing how it interacts with curvature. But in this class, our spaces are flat, so that's not a big deal. And in particular, I have function f, which is defined on the whole plane, but I only want its derivative in the v direction. Okay, so there's a pretty reasonable way that I could define such an object, I would argue, which is as follows. Like the limit as h goes to 0 of f of x plus hv minus f of x divided by h, like that. Notice it's just definition of derivative, but I'm kind of like taking like a one-dimensional slice of my function like that. Yeah. Students that hang out in my office long enough will recognize that this is also the way we go about defining something called the functional derivative or Gateau derivative in fancy spaces. Okay, so let's say that I plug in the Taylor series for f. What am I going to get? Well, remember that f at x plus hv is roughly equal to f of x plus h times df at x b, right? That's the linearization of that, yeah? So in particular, if I plug that in, and remember the Taylor series hold for small h, so that's a good news. If I plug that in here, what I'll find is that the directional derivative is equal to df evaluated at x times the vector v. Okay? Now, why does that matter? Essentially, what Broyden's method is going to do is going to say, well, I don't have access to df, but I do have a reasonable way of approximating df times v, where v is specifically the vector between the previous iterate and the current one. And so this is like a one-dimensional, now we've got like a little toehold into the secant method, which is we're going to like draw a secant through this one direction and say, at least in this one direction, we expect df to kind of look like the slope through those 2 points. We're going to formalize this mathematically in a second. Okay. So here's going to be the idea. So here, I'm going to call j my approximate Jacobian of my function, right? And essentially, if we take this schematic that I've drawn here and we translate it to something that looks like the secant method, what I might say is that if I take my Jacobian and I multiply it by the vector between the last 2 iterates, that's the left-hand side, then roughly what I should get is the difference between the values of those 2 points. Notice there's no h here because I didn't divide xk minus xk minus 1 divided by h. I just kind of scaled both sides. Does this approximation make sense? This is saying I don't know the Jacobian in every direction, but I do expect a reasonable Jacobian limited to the line between my last 2 iterates to kind of predict the difference between the function values. This is called like Broyden's approximation here. Isn't this sneaky? Now, is this relationship enough to determine j? Let's do some degree of freedom counting. So j is n by n. So there's n squared kind of unknowns for the Jacobian at iterate k. This is kind of n relationships if I do this row by row. So this is an underdetermined problem, right? And so we don't yet have an optimization algorithm. We just have some conservative approximation of like a thing we hope to be true. Cool? So there's still a little bit of engineering though that we can do here. And in particular, here's what Broyden's method is going to do. It's really sneaky. I love this algorithm because it's like a cleaner version of BFGS, which is horrifying. In fact, the first edition of my book has a really bad proof of BFGS, but I've streamlined it a little bit since then. Okay. So here's what Broyden proposed is the following. At every iterative of my algorithm, I'm going to maintain two objects. One is xk, like my current guess of where the root is. But now I'm going to keep around a second object, which is jk, which is the current guess of the Jacobian at xk. Okay? And essentially what this algorithm is going to do is going to ping pong back and forth. It's going to update x, and it's going to update j, and it's going to update x and j. Right? And in particular, here's going to be the trick for finding jk, is we're going to solve, because in this class this is what we do for literally all problems, we're going to solve a least squares problem. So in particular, we're going to find jk to be an optimization problem. This is, by the way, I think the first time in this class we've encountered a problem where the variable is a matrix. So like, put on your seatbelts. Where we're going to say, okay, well, I might as well, just out of kind of laziness, say, well, I've got my previous j. If I don't have additional information, I should leave it alone. Right? So I'm going to say, to get my current jk, I guess technically this is the R command for one of you people raises your hand. I'm going to say, okay, so in directions where I don't have any information, just leave j alone. But I now got one additional piece of information, which is in the secant from xk minus 1 to xk, I want to update j. So in particular, I'm going to add a constraint, which is that j times xk minus xk minus 1 equals f of xk minus f xk minus 1. Does everybody understand what this is doing? So this is what Broyden's method is going to do. It's going to update j by solving this optimization problem, and it's going to fix j and take a Newton step to get the next x, and then it's going to update j again. Cool? In fact, here's an outline. Ta-da! Okay. So, right. So let's now do a little bit of ugly math. I'm so sorry. Again, like, pay attention to this one because the BFGS one's worse. Okay. So, in particular, let's define delta j to be equal to this difference, j minus jk, just to like simplify our notation a little bit. Similarly, we can define delta x and so on. Okay, so in our new language, we're going to have that we want to minimize the norm of delta j squared. By the way, we're going to use the Frobenius norm in this proof. A totally reasonable question is, what about like a spectral norm? And I actually don't know the answer to that. I think most likely you'll get the same formula, but I'd have to think through it a little bit. Okay, so we have delta j times delta x, so that's kind of good, is equal to, we have to be a little bit careful here because remember that like j is equal to a constant shift of delta j. So we have to rearrange this expression a little bit. We're going to get f of xk minus f xk minus 1, just like before, minus jk minus 1 times delta x. Right? And that comes from the fact that I've like shifted my problem by jk minus 1. Sorry. Okay. This looks ugly, so let's give things a name. I see it. So we're just going to call this thing d. Good news is we can compute it. Okay. Questions? I saw your hand. Yeah. This guy here. So we made this substitution here, right? And so we need to account for the fact that essentially we now have a shift in delta j. And so this guy gets multiplied by delta x. And that's what we've moved to the right-hand side. Yeah. Okay, so cool. So there's our optimization problem. Essentially minimize the norm of delta j subject to a constraint that multiplied by delta x, I get d. By the way, this is like a good life hack. It's just like this is an optimization problem that shows up a lot. Like, don't change a matrix too much except on one slice. Does anybody have a guess of what's going to happen? Maybe it's like taking a fancy linear algebra class. Is the action of j in directions orthogonal to delta x likely to change? No, right? Because we kind of don't have any information there. So essentially what we're going to show is that this is a simple update to j. Okay. So, it's important not to think too hard. So, in particular, let's just write down the Lagrangian of this darn thing and take its derivative. This is good midterm review. And it's a good way to start messing with your brain where you're thinking about optimization problems whose variable is a matrix, right? This is fancy math. So in particular, what is Lagrangian? So we've got a variable, delta j, and we've got a constraint. Notice the constraint is actually a vector worth of constraints, right? One per row of this matrix relationship here. So in particular, for some reason the textbook doesn't put a 1/2. I guess I'll do the same and end up with a bunch of 2's. That's fine. I complain about the textbook as if it's someone else's fault. Okay, so we've got the inner product between our Lagrange multiplier and the constraint. So this is delta j, delta x, minus d. Okay? Hopefully this is becoming kind of mechanical. You take some optimization problem, you're right, it's Lagrangian, you start differentiating with respect to all this stuff, right? This is a good one to practice at home. Okay, so we need to differentiate this bad boy with respect to delta j. Yeah. So what are we going to get? We will get 0 is equal to the gradient with respect to delta j of our Lagrangian. Okay. Luckily, this gradient is not too complicated. So in particular, this is just the norm squared, right? It's like the sum of the elements squared. So this is going to be 2 delta j. Notice our gradient is a matrix in this case because our unknown is a matrix variable. The second one is a little bit tricky to think about. We're going to get lambda delta x transpose. So this is basically differentiating this term here. This feels annoying because of like a delta j sandwiched between two other things. There's a lot of different ways to justify this formula. Either you can just do it element by element. By the way, on your exam, if you're panicking because you're uncomfortable with matrix calculus, it's perfectly fine to do the index version of this. You shouldn't because I'll judge on you a little, but as long as you get the right answer, it's fine. So the more fancy grown-up one is to notice that this is a scalar, right? Lambda transpose delta j delta x. And remember that scalars are equal to their own trace. This is like our favorite trick. So this is the trace of lambda transpose delta j delta x. And then we can cycle traces around. So this is the trace of, which way do I want to write it? How about delta x lambda transpose delta j? Like that. Cool. Which is the trace of lambda delta x transpose times delta j, like that. And you might recognize this. This is a formula for the inner product, just element-wise, of two matrices. So notice this is a linear expression in delta j. It's being dot producted against this guy, which is what gives you that. Cool. If that went by a little fast, I'll ask you to trust me for now, but you should check it out. Okay. So, right. So in particular, notice we're cooking with gas here. We have delta j just like by himself, or itself rather. And in particular, what we conclude is that delta j is equal to 1/2 with a minus in front of it times lambda delta x transpose. Cool. We're getting there. We don't know lambda yet, but like, notice that we actually learned something, which is that the change between j and its previous iterate is just like an outer product of two vectors. This is called a rank 1 change, which is kind of unsurprising in retrospect, but it's good we double check. Okay. So now we got to solve for lambda. How are we going to do that? Well, we know that j times delta x is equal to d, or rather, delta j, let's write it this way, is equal to like that, right? This is our constraint. So now we can plug in our expression. So in particular, delta j is minus 1/2 lambda delta x transpose delta x. Cool. You guys see anything kind of cool that just happened here? Let's parenthesize our expression like that. This is just the norm squared. This is one of those proofs where just like magic things happen. By the way, we're about to divide, and one question you should always ask when you divide is like, can I divide by 0? Notice that like this algorithm kind of doesn't make sense. If delta x is equal to 0, then like the constraint is meaningless and I should just remove it. Yeah? Okay. So in particular, we can conclude that lambda is equal to minus 2d divided by the norm of delta x squared. I did that without looking at my notes. Do I agree? I do. Good. Okay. So, of course, what we really wanted is not lambda. We wanted delta j. So we need to continue to unravel our arithmetic ever so slightly. Is it okay if I erase just this bottom portion? Okay. So in particular, what did we find? Well, we know that delta j from up there is equal to minus 1/2 lambda delta x transpose. We got a lambda there, so the minus 1/2 and the minus 2 cancel. And we're going to get d delta x transpose divided by mod delta x squared. If I glance at my notes, ta-da, they agree. Excellent. So do you see what happens in Broyden's algorithm, at least like version 0.1 that we're going to write down? So essentially, we take a step, right? That gives us a new x, so now we have a new delta x and d. And then we take our old j and we just add this thing to it. That's really it. Kind of neat, huh? So there's our expression. If we unravel things a little bit, we made a bunch of definitions. Then there's the formula in its full glory. It's kind of ugly, but now you guys see where it comes from. Cool? All right. So what do we do in Broyden's algorithm? Well, we update j, and now we take a Newton step, so then that's the next thing that we do. So what's the time complexity of this algorithm as we've described it? Yes? Nope. What's the time, or like, what's the time complexity of a single step, rather? One more try. It's cubic, right? I got to solve a linear system of equations. So somehow I didn't actually solve all the problems that I set out to solve when I defined this algorithm, right? Like I still have a j inverse though. The j isn't the Jacobian anymore. Somehow it feels a little more stable because it feels like secant method. In fact, in 1D you can check this is the secant method. But I haven't actually solved my problem, right? I wanted something that didn't require so much work per step. Yes, question? No question. Cool. All right. So let's sanity check a little bit. And then we're going to see that a really magic thing happens in Broyden's method, which is that actually the time complexity of this thing is far less than it might appear. Yes?
If I'm updating every time with a random matrix and I need the inverse of this, do you not use the iterate update?
That's a great question. That's exactly what we're about to cover. Yeah. So there are a couple implementation details we should cover first. So the first one is how do we initialize J naught? There's no right answer here. I think typical choice is just the identity matrix. We'll see why in a second. Is there any reason why that should be the slope of your function? Not really, but it's enough to get things started. Notice that like what's going to happen in this algorithm is the first couple steps are going to be really bad, right? Because I have a bad Jacobian approximation. But as I do that, I'm evaluating f at a bunch of points, and I start to be able to build up my Jacobian. Yeah? There's also one additional issue, which we're going to come back to in a minute. If I run this algorithm long enough, like especially let's say that n is really large, so like I'm in very high dimension, then there's actually this sort of weird issue with this algorithm, which is it has a very long memory. Notice that like I only update my matrix J and like a one-dimensional slice in every step. So like if I've got like a billion by billion matrix, it'll be like a billion steps before I remember I completely forgot the iterate a billion steps ago. Right? And that could be a problem because like in some sense we intend for J to be an approximation of the derivative of our function, but somehow it's like remembering stuff from like long ago in our procedure. So both of these, so somehow this doesn't feel like the right thing. So we're going to talk about two tricks. Our colleague suggested one, which is essentially a faster way to compute the matrix inverse. And then once we have that in hand, we're going to see that in fact we can do even better than that and only construct a Jacobian from the last couple steps of our algorithm. Right? Like so for example, a very naive thing that I could do to address that second problem would be keep around the last 50 iterates, right? And then build up J by doing this approximation 50 times. And then just kind of have like a sliding window of those things. But that's of course very expensive. And we'll see that there's a very efficient implementation of exactly that. Oh no, I gave it away. Okay, so essentially we've got a lot of complaints about this algorithm. Like we did a kind of interesting thing. Notice that we no longer need to differentiate f, so that feels kind of good. But we don't know that this algorithm actually, you know, works terribly well. Like it feels like it takes a lot of time per step. Okay, so let's see if we can address that. And in particular, essentially, let's take a look at our Broyden update. If we want to, we can do a little bit of code factoring here, and we can just call these two vectors that go into this calculation u and v. Right? So basically, in every step of Broyden's method, my Jacobian gets updated by some expression of the form uv transpose, where u and v are just extracted from the previous thing. And somehow, the thing to take away here is that this is a simple update to our matrix. Notice that, like, if you think about what your matrix is doing, right, like as its action on a bunch of different directions, if I take any direction orthogonal to v, the action of my matrix actually didn't change. So somehow the inverse in a lot of dimensions feels the same. It's only in the one dimension of v where I need to be a little careful. Yeah? Oh, there's a typo. That should be k minus 1. Thank you. Yeah, on the right-hand side. My apologies. Somebody please send me a message on Piazza and I'll fix it in the slides. Otherwise, these things persist for, well, let's see, these have been used at least 8 times now. Yeah, good catch. Okay. So, as our colleague suggests here, luckily for us, there's going to be a beautiful formula from linear algebra that's going to come to our rescue, which is that it turns out if I have a matrix of exactly the form on the bottom of the slide, there's actually just a formula for its inverse in terms of the inverse of J. This is often called the Sherman-Morrison formula, or Sherman-Morrison-Woodbury, or Woodbury identity. These are all slightly different formulas, it turns out. If you want to like track down the academia, like who owns what piece of this formula, you probably could. But essentially, this formula tells you the following, that if A is an invertible matrix and I add a rank 1 change to it, the formula on the right-hand side is the inverse. Is this formula obvious? Absolutely not. Now, we're going to omit the proof of this formula. It's in the textbook. Does anybody have an idea for how to prove this formula? It's important not to think too hard. That's right. So like basically, if you ever want to check if two matrices are the inverses of each other, you just multiply them together and see if you get the identity. So you can do that here, and you'll just end up with a billion terms that cancel. That's all. Right, so this is an extremely useful identity. It shows up all over the place in numerical linear algebra. In fact, if you look backward, if you look at, for example, our LU factorization, you could ask what happens to LU factorization if I add a rank 1 update to a matrix. And it turns out this is also the formula that's behind a lot of algorithms there that like dynamically update LU as you change your matrix. So this actually suggests a very different algorithm for Broyden's method, although it does violate a little bit of like it looks like a cardinal sin of numerical analysis, which is do the following. Rather than keep around J, I'm going to keep around J inverse. Why would I do that? Well, in Newton's method, remember, I didn't actually need the Jacobian. I just multiply by the Jacobian inverse, right? And so why might I initialize my Jacobian to the identity? Well, the good news is the identity is a matrix whose inverse I know. Anybody want to hazard a guess? Also the identity, thank you. I just want to make sure you're awake, that's all. And what I'm going to do is as I step through Broyden's method, I can essentially update not J, but J inverse using that Sherman-Morrison formula, right? Notice that these algorithms theoretically are 100% equivalent to one another, right? Like I'm maintaining a different matrix, but the iterates xk I get are exactly the same as Broyden's method with an inverse in every step. You can check it numerically. Now, the question that always comes up here is like, why is it okay to keep the inverse of a matrix around? You told me that's dangerous. And indeed, I tend to agree. In this particular case, I think it's sort of safe for a few reasons. One is that Broyden's method takes big steps. So some of like the really wild and crazy derivatives that you see in a noisy function get smoothed out a bit. So these like J inverse doesn't tend to be gigantic. Moreover, if J inverse is really large, Newton is going to probably take a step and diverge anyway. So there's kind of a larger issue. But this is all to say that you have to be a little bit careful. You are maintaining the inverse of a matrix. And for example, like we asked earlier, if it's singular at the root, you really could run into trouble. Now, if you remember, like in Newton's method, we talked about in order for Newton to converge, we actually need f prime to not equal 0. So like in particular, Newton's method does not necessarily converge quadratically if your function kind of looks like that. And you can see that failure mode kind of reflecting itself here, like you don't have an inverse in your Jacobian. All right, I saw a hand, but it was in my periphery. Yes? Yeah. Oh, that's a big problem. Yeah. You guys are thinking critically today, and that's fabulous. So that suggests our next algorithm. Sadly, we're a little low on time, so we'll skip some of the details. Which is as follows. So we've now noticed that we're kind of doing like a whack-a-mole kind of situation. Like we've, what have we done? Like we started with an algorithm that essentially feels like it's got the same complexity as Newton's method and is worse because we don't have a derivative. And then we noticed that we can kick it down from cubic to quadratic by using this thing, right? Because now we just need a matrix multiply. We update J inverse, and that's quadratic time, or even less, I suppose, if you use one of these useless things in CS theory. So the question is, can we do any better than that? And notice I had a third complaint earlier, which is that like Broyden's method, the Jacobian can get stale, is the term you hear a lot in practice, meaning that like Jacobian remembers iterates, you know, like Pepperidge Farm remembers. Like you have like this long trail of iterates that are informing your formula for J, and it's only updating it in like 1D slices. So it could easily be the case that some slices of J are from like 1,000 iterates ago and really don't tell you anything at all about like the landscape near your current point, right? And so one way that you might get around that, if you don't care about computational efficiency, would be as follows, to basically, as I mentioned before, like just keep around like the last 10 iterates, for example, and kind of build up J for 10 steps using this formula from the identity and then apply its inverse or something like that, right? Now, that solves the staleness problem, but it introduces two new ones. I mean, so for one, now the time complexity of every step is a lot higher. And moreover, our colleague's absolutely right that like, I mean, our matrix, like J inverse is a big dense guy, and we don't really want to keep that around. So here's a really cool thing. If you look back at this Sherman, Morrison, Woodbury, whatever identity, this guy, I can apply it recursively, right? So in other words, like it doesn't have to be for a rank 1 update. It could be for a rank 10 update. And I'm going to have like basically a bunch of changes that look like this formula here, just like one stacked after the next, right? So here's a really cool thing to do, and this is called the, I think people call this the L-Broyden algorithm, which is not so common. There's another one called LBFGS, which is extremely common and uses the same trick. But what you're going to do is you're going to unroll this formula here. So in particular, like let's say that I have, just to give you a little bit of an idea, we're not going to do this in great detail because it's like the kind of thing that's easier in code than on a blackboard. But just to do 2 steps. Okay. So here's the kind of thing that I could do. Let's say that I started with the identity, and then I start building up my Jacobian, right? So in essence, if you think about like just remembering the steps of Broyden's method, in essence, my Jacobian takes the following form, right? Like that. Does that make sense? And that's certainly true in Broyden method, right? So in Broyden method version 0, this sum is all the way from the first iterate till the current one, or we could imagine a version that just looks in the last couple iterates. Now here's the thing that I could do. Let's say that I have, this is like I equals 1 to L, like that. And I look at its inverse. Well, obviously this is I plus some I equals 1 to L minus 1 of UK VK transpose plus UL VL transpose inverse, like that. You see what I'm about to do? Well, I can apply this formula now, right? And what am I going to get? Well, all right, I'm lazy. Let's call this thing M. Like that. Right, so I'll get that this is M inverse plus M inverse UL VL transpose, and then we got another M inverse like that divided by stuff, right? This guy is just the same as the last one, but with one term lopped off of it, right? So what I can do is apply this formula recursively, right? Until I get back L steps, and then I just sub in the identity. And that's what the L-Broyden method does, is it just keeps around, rather than keeping around J or J inverse, it keeps around this list of UV terms for the last couple steps of the algorithm. And it essentially just expands a big, ugly version of Sherman-Morrison formula in that particular case and applies it directly. The good news is that, I see, essentially what you'll find is that the time complexity looks like the product of the number of steps that you took and the size of your problem. So it's like L times n, which is a lot smaller than n squared. Yeah?
In order to do this, we have to go all the way back.
Yeah. All the way back to the identity.
So,
It's turtles all the way down.
so, like, can we store something along the way so we don't have to keep going?
Oh, absolutely. That's why I'm not writing this whole expression out. Like, this is one of these things you do in code. You like write a recursive piece of code that unravels this formula. Or there's just a version of Sherman-Morrison formula that accounts for a rank K update as opposed to rank 1 update. Either one of those is okay. Yeah. So I'll let you guys read about the details. But the basic high-level idea here is that you kind of construct the Jacobian just out of the last couple steps of your algorithm, and then it's not too stale. And moreover, your storage is relatively low. And that way you kind of have this like sliding window of steps that informs your J. Really sneaky algorithm. Cool? I would say Broyden's method isn't like widely used in practice, mostly because root finding isn't all that widely encountered problem. What we're going to do next in this course is talk about optimization, which is of course the problem that we all know and love, where you're trying to find the minimum of a function as opposed to where that function crosses 0. And for differentiable things, those two guys are very closely linked to one another, right? Because as we all know, what is the first thing we do in calculus class if we want to optimize a function? Yeah, take the gradient and set it equal to 0. Well, what did I just do? I took an optimization problem and I converted it to a root finding problem, right? So for example, if you look at Newton's method for optimization, right, you might remember that's like Hessian inverse times gradient. Well, that's exactly the same as Newton's method for root finding. It's just you like bumped up your derivatives by 1, right? And so what we're going to see is that basically all the root finding algorithms we've talked about here translate very cleanly to optimization techniques, just with one more derivative kind of floating around. Yep. Now, I can't help but preview a little bit. Where does Broyden's method go wrong if we want to do optimization? So again, our next step in this course is going to be to solve problems that look like min over x of f of x, right? Which, of course, from calculus kind of means I might solve this root finding problem. Yeah. So from here, like, what is d of grad f? Like, what is the Jacobian of the gradient function? Okay, so gradient is one derivative. I take the derivative again, and the Hessian. That's right. So like this is a very fancy way. Is the Hessian of f, like that, right? That immediately suggests an optimization algorithm, which is to find roots of this guy, which is to say x gets x minus hf x inverse times gradient of f. Notice this is just Newton's method applied to this root finding problem. That's all it is. And in fact, like this is the algorithm we're going to spend all of our time analyzing. So we already kind of talked about it. Now, a reasonable question you might ask is like, does Broyden's method apply then? Now for updating like kind of an approximation of the Hessian. And the answer is, yeah, you could use it, but like it's not entirely realistic. Does anybody see why that might be? Let's think about H for a second. What do we know about Hessian matrices? They're symmetric. Somebody said positive definite. That's often the case, but we don't know that going in. But we do know that if I differentiated I and then j, that's the same as differentiating in j and then I, which is basically the same as saying Hessian is symmetric. By the way, drawing a geometric picture of that like little fact that we all know from calculus is like shockingly difficult to do. It's like something that we all check algebraically. But in any event, notice that Broyden's method does not maintain symmetry, right? Like, so if I start with the identity matrix and I start doing these little rank 1 updates of this form, then in one step, your Hessian approximation is going to be kind of weird. So you could use this method, but essentially what we're going to do is derive a whole sequence of methods where essentially, rather than just solving this, this optimization problem here, we're going to add an additional constraint, which is that j is symmetric. And that's going to lead to an algorithm called DFP, or Davidon-Fletcher-Powell. And then we're going to replace our norm with one saying, well, why did I use this lazy norm? Like, even if j changes a little bit, it could be that j inverse changes a lot. Like, for example, the difference between 0 and epsilon. So maybe I should really evaluate the norm on j inverse. And that's going to lead us to the BFGS algorithm. So just as a quick kind of preview of what's going to happen. Okay, so in any event, essentially what our next big segment of this course is going to be on is optimization. And I really view what we've done so far in root finding as just kind of a warm-up for that, for exactly this reason here. Any questions so far before we dive into some examples? Yes? Oh, yes, but we're nowhere near talking about that quite yet. Yeah, so this algorithm is not going to work terribly well um, if my function is not bowl-shaped. Notice that that's also the case for Newton's method, like for root finding, like if our slope is kind of not suggestive of the root I'm trying to find, I get in trouble. Okay. So, right. So essentially, one thing you guys might have noticed, this is a bit of a modern perspective on numerical analysis, and it's certainly reflective of my own biases as a researcher here at MIT, is that I've tried to introduce almost every numerical problem we've talked about in this course in optimization language. Right? If you like crack open like Trefethen and Bao or like one of these old school numerical methods books, that's often not the case, right? And of course, it's certainly the case that numerical algorithms show up everywhere and not all of them naturally come from optimization. But I do think it gives us a nice framework, right? And so we already actually have a whole table of optimization problems that we solved in this course, right? Everything from like, least squares to projection to finding eigenvectors. In that case, you need a constraint. Computing pseudo-inverses, and so on, right? I guess this table is a little weird because I forgot to put the constraints in, but whatever. And in fact, in our Broyden problem, we even derived the Broyden algorithm as itself like a little mini optimization problem in every step, right? And so that suggests that optimization is really, really important. And I don't think anybody in 2025 would deny that in a computer science department. Of course, these days, our AI overlords are basically doing optimization all the time, burning through the rainforest on a daily basis. So it's important to understand what these algorithms are like so that we can make them more efficient and stable and so on. Of course, in these particular problems, some of them also have constraints. And in this class, we'll talk about optimization with and without constraints. Right? So for example, in the eigenvalue problem, remember that we optimized x transpose x subject to the constraint that x has norm 1. So this is all to say we've actually already done a bunch of optimization in this course. And if we are so lucky as to our problems falling into one of these categories, we know how to solve it. Now we're going to talk about the generic case where like we're not so lucky. And of course, what do you think our strategy is going to be for deriving algorithms? We've got this big table of problems we know how to solve in maybe not closed form, but like in ways where we have very efficient algorithm. So if we can approximate our problem with one of these guys, we're in pretty good shape, right? And in fact, that's basically what Newton's method's doing. So in general, I think if there's one really critical skill that all of you guys can get out of largely graduate school in 2025, I would say one of the key ways that people go about modeling, which is a little bit of a development in the last 10 years, is to think in a sort of variational fashion. This word variational, I think, comes up a lot. It just means like using optimization tools. Comes from fancy. I think it's one of these cases where computer scientists thought optimization didn't sound fancy enough, so they like borrowed a term from like infinite dimensional stuff, even though we never do that. But in any event, essentially the idea here is that like in old school computer science, like if you took like an undergrad algorithms class, I had to teach it a couple years ago, which was hell for me because it's not my universe. You're like talking about sorting numbers and processing graphs and computing shortest paths. You don't necessarily think about these as like numerical problems, right? You think of these as like I have a very particular thing I'm trying to extract from a discrete object. But in a lot of modern algorithms, including some of those problems, you can express it as an objective function and then try to optimize. And in fact, there's a really beautiful equivalence that like this even broad class of just algorithmic problems in computer science can be written this way. And in fact, if you talk about the time complexity of our optimization techniques, it can give some pretty good ways to solve even classical problems. We're not going to talk about that a whole lot because this class is more kind of applied, I guess, by computer science theory perspective and less applied from a mathematician's perspective. But all to say that this is a very modern perspective on even very classical problems. Now, so far, we've talked about problems where the optimum has some closed form formula, right? So like what's been our optimization algorithm so far is to like take the Jacobian by hand, like squint at it, stand back 10 feet, philosophicate, and then like try to find a formula. But sadly, that doesn't always happen. And so in the next many lectures of this course, we're going to talk about all kinds of optimization techniques that apply to different forms of functions f. So we're going to start out with the simple case, which is unconstrained optimization, largely when f is differentiable. And in fact, we're going to start algorithmically by talking about the one-dimensional case. Now, we're a little bit low on time today, so I don't think I'm going to talk about some algorithms. I'll just give you some pointers to discussion in the book. The good news is that I think at this point in 2025, you guys don't need a lot of motivating examples for optimization problems because this is just the dominant way that we do modeling in computer science. But just to give you a few, there are many. So for example, if I want to fit a statistical model to my data, let's say that I have a data set of XY pairs and I expect that to be exponential, right? Then I can set up a least squares problem just like I did in our lecture on linear least squares. But sadly, thanks to that E, my problem is no longer linear. So when I set up this least squares problem and I try to minimize it with respect to, in this case, just A and C, sadly, our algorithm from before just doesn't apply. We don't have a closed form formula. So, these days probably we replace the exponential with a neural network, and then what you get is supervised learning with a least squares loss, which is exactly the kind of problem we study quite a bit. For example, in statistics, in maximum likelihood estimation is actually basically equivalent to the previous one. These kinds of problems come up. There are other kind of fun ones. So for example, in geometry, if I have a bunch of points in the plane and I want to compute some version of the median, for fun, I added to the textbook some discussion of this like weird little optimization problem. Now, if I minimize the sum of the squares, I get the average of the xi's. Here's a kind of fun thing you can do is say, what if I want to do least squares, but I don't square every term? I just take the absolute value. Or in multiple dimensions, I take the norm, but I don't square it. Yeah. The one thing you can convince yourself is that this is actually a very robust problem, which is kind of cool. So the textbook has some examples. For example, in one dimension, I could write the following optimization problem, which is min over x of the sum of the absolute value x minus xi, like that, right? So we know if this is squared, we actually proved in class this will give the average of the xi's. It turns out one thing you can prove, this only happens in one dimension, but in one dimension, I kind of like lay out my xi's on the line. Then, well, I kind of expect x to be in the middle, but it turns out it only depends on the median of my data set. So this is a very robust way to take an average. Right, so in any event, if you look through the book, there's a broad variety of applications of optimization. I think it's not that hard to find them in your everyday life. To give a bit of language, though, we're ready to talk about algorithms in our next lecture. The typical drawings that we're going to draw, a lot of are pictures like what we see on the screen here, right? So we have our horizontal axis is x, and we're trying to minimize f. So we're no longer trying to find roots like crossings here, but rather we're trying to find points where it's minimized. Oftentimes, in numerical methods, we ally to the fact that we might only been able to extract something called a local optimum, which is like this point on the left, where in some little neighborhood around that point, it's not obvious that I can make my function any smaller. But of course, if I look at a bigger neighborhood, now I can see that I can make a big jump to the right-hand side. So if we want to define these objects mathematically, then we can talk about the global minimum, which is to say that f of x star is less than or equal to f of x for any x, right? This is a strong condition. Or a local minimum, which is basically just saying that like in some little neighborhood, it's less than or equal to. Okay, so maybe we'll pause there. In our next lecture, we're going to basically derive lots of optimization algorithms. We're going to start out with a little mathematical puzzle that I want to leave you guys with today, rather than doing what I usually do and rushing through content, which is as follows. So I think all of us in 2025 are familiar with at least one optimization algorithm called gradient descent. Right? What does gradient descent do? It takes my function f of x, it computes its gradient, and then it steps a little bit along, you have to be careful, minus that gradient, and then it replaces x, right? And now I think if I ask 80% of the students in this class, well, why gradient descent? You say, oh, well, the gradient is the direction of steepest descent, right? In fact, oftentimes people call gradient descent like steepest descent algorithm. Here's my puzzle for you guys. Did you ever actually check that fact? In other words, like gradient descent, the reason we use it is that apparently the gradient points downhill, and there's no other direction that points downhill faster. Right? That's our intuition. Well, get out some scrap paper, actually check that fact. And I think what you'll find is a little bit of a puzzle. It's not a huge puzzle, but it's actually one of these things that I think we all take for granted and is the basis for all our optimization algorithms, and itself is already not immediately obvious. It's the kind of thing that we have to check. Okay, so in our next class, we're going to start with that. And then we're going to derive one-dimensional optimization problem just for fun, which is called golden section search. The kind of interesting question you should ask there is, what would it take to make bisection work for optimization problems? Which is also not an obvious thing. Yeah. And then we'll move to all kinds of fancy high-dimensional stuff. Okay, so with that, everybody have a delightful rest of your Wednesday. We will see you on Monday, and then we'll see you on your midterm. And for every one of you guys that we don't see in class on Monday, I'm going to make your midterm a little harder. Okay.